Hello dear students, we are quickly revising the TYBSC paper 2 semester 6 practical sessions, that is experiments in University of Mumbai syllabus. This is a quick revision for the sake of understanding in view of forthcoming practical examination. There are two sets of experiments as the general outline shows here. First part is inorganic preparations, total 3 preparations included in your syllabus, and the second set is quantitative and qualitative analysis. 3 preparations included are tris acetyl acetonato ion 3 complex, second one is nickel dimethyl glyoximate complex, and the third one is potassium trioxalato aluminate complex. All the three are coordinate complexes. The second set of experiment that comprises of percentage purity determination of the supplied inorganic salt, and of course identification of cation and anion from the impurity salt which is mixed with the major component. So there are quantitative analysis of magnesium, barium, calcium and strontium. There are total 4 metal ions. Out of that 3 are expected. All are bivalent metal ions. So estimation of magnesium, barium, calcium or strontium by complexometric titration method is expected, and qualitative detection of impurity cation and anion includes NH4 plus and K plus as the impurity cation and anion which are mixed with the major component. Now both the impurity ions are to be detected by wet test method, that is by preparing water extract, and of course the students are supposed to know the detection of major ions, that is magnesium, barium and calcium, that is the detection of these major component ions by wet test method. Trisacetyl acetonato ion 3, this preparation of complex is of course, as it is said, it is based on green chemistry principle because it obeys the following rules, that is it is less hazardous chemical synthesis, it requires very low temperature, and there is no evolution of poisonous gases, no vigorous reaction, minimum waste, no byproducts, hence it is based on green chemistry principle. Now here basically, metal acetyl acetonatos are highly efficient catalysts. So their application, it is used in organic transformations such as polymerization, hydrogenation, coupling, etc. They are also used in rubber technology, fungicides in pigments as color stabilizers. Now here, one thing all should know that acetyl acetone, here it is a dione and it has two linkages with the central metal ion, and it is forming a stable complex, that is tris acetyl acetonato ion 3 complex. The question arises why it is acetyl acetonato, not acetyl acetone. The reason is because acetyl acetone, here it ends with the complex has a negative charge, and therefore it is acetyl acetonato ion 3. One should know the requirement, that is which are the starting material. Here we require one metal salt, that is ferric chloride, which should be anhydrous, and the second one is a ligand. We are using acetyl acetone as a ligand. Now here metal ion, you should all know that Fe, it is in trivalent state, that is plus 3 state, and it interacts with ligand acetyl acetone to form a stable crystalline complex. The color of the complex is very bright red and it is crystalline. The method, it is carried out by two methods actually. Employable methods are two. One is using the solid FeCl3 and one is using solution of FeCl3. If we are using solid FeCl3, one has to dissolve it in minimum quantity of distilled water. Then the whole procedure is carried out by keeping the reaction mixture in ice bath, because it adheres to the green chemistry principle, which requires that reaction is carried out at low temperature, and hence the entire method is carried out at low temperature. This is the beauty of this preparation of a complex. Filtration purpose, we are using Wattmann filter paper 41. So filtration is carried out through Wattmann filter paper 41, and of course the complex is dried in open air for 15 to 20 minutes, and then the weight of the complex. Look at the image of the product form, which is brightly red color complex, and this complex is very stable. You can check by having a look at the structure, where Fe in 3 plus state at the center, it is surrounded by 3 units of acetyl acetone. The total complex geometry is octahedral. There are 6 equivalent FeO bonds. You can check it from the figure that Fe at the central position and is linked to total 6 oxygen atom. One acetyl acetone unit is linked to central Fe by 2 oxygen atoms as the donor atoms. So there are 2 points of attachments for each acetyl acetone unit. Total number of bonds are 6, out of which 3 are coordinate and 3 are covalent. When there is a coordinate bond, indicating that lone pair of electrons are transferred from oxygen to Fe. Observations and calculations. Here we will have to note the weight of the empty Wattmann filter paper, then Wattmann filter paper weight plus complex, which is weight. From that one can easily find out complex, and then finally result to be written, that is percentage yield complex, by following this mechanism of calculation. For calculation there are again two parts, theoretical yield and percentage yield. Theoretical yield, to calculate theoretical yield one should know the molecular weight of the complex. The molecular weight of the complex is given, and from that you can find out theoretical yield. Once theoretical yield is calculated, using that, percentage yield can be find out by knowing the weight of the complex. Second preparation, that is from the syllabus, nickel DMG complex, nickel dimethyl glyoximate complex. Again, this second preparation is also based on same principles, that is green chemistry principle, but again the salient feature of this complex is it is solvent free analysis. There is no addition of water, no addition of acid, or no addition of any basic medium reagents. It is less time consuming. Very quickly you can find out that the complex is formed by simply addition of metal and ligand in solid state. So this is again the one of the remarkable feature of this complex, that entire reaction is carried out in solid state. No byproducts are formed and it is highly eco-friendly. One should know the starting material. Here we are using nickel carbonate. It is an anhydrous form, and the ligand is dimethyl glyoxime, which is an organic reagent. Simply mixing of the two reactants and keeping it in oven, heating at controlled temperature, gives us the pink red solid product. Molecular weight of nickel DMG complex, and of course after knowing the weight, that is W, unknown weight, which is supplied to you by the examiner, you can calculate the percentage yield. Now coming to the structure of the complex, again nickel, which is in bivalent state at the central position, it is linked to 2 units of dimethyl glyoxime, and therefore the name is nickel bis dimethyl glyoximate, because bis means 2, there are 2 dimethyl glyoxime units. When it is oxime, there is NOH as the functional group, so one can check here there is hydrogen bond, and therefore total number of rings one can see in the structure, that is 4, and there is seen hydrogen bonding. Out of 4, 2 are pentagonal rings and 2 are hexagonal ring. Now one salient feature that we have to note, that 2 equivalents of conjugate base of DMG, they are interacting with the central nickel plus 2. Okay, and therefore 4 rings are observed. Of course, the color of the complex, it is prominently seen from the image which is here. Observations same as the previous one, and calculation, one should know the molecular weight of the nickel DMG complex. From that, theoretical yield will be calculated. Once it is known, then percentage yield can be calculated by knowing the unknown weight of the one. And finally, result. Coming to the third preparation, potassium trioxalato-aluminate. Now here it is also known as potassium trioxalato-aluminate trihydrate, because it is always associated with 3 water molecules. Here again metal ion is aluminium and it is in trivalent state, that is 3 plus. The ligands are oxalate anions from oxalic acid. Now here it is a little bit tricky complex. There is no direct interaction between the aluminium salt and the oxalate ion. Basically, aluminium ions, that is from the given metal salt, are brought into hydroxide form first, that is by interaction with potassium hydroxide. KOH, potassium hydroxide, serves 2 purposes. One is it provides potassium ions that we can see located outside the coordination sphere as K3, and second purpose is KOH reacts with oxalic acid and it forms a product potassium acid oxalate. Now this potassium acid oxalate becomes the main reactant which reacts with aluminium hydroxide, and finally the reaction between these two leads to formation of a complex, that is potassium trioxalato aluminate. This is the structure showing aluminium at the center. It is linked to, as the name itself suggests, that it is linked to 3 oxalate groups. So you can see 3 oxalate units. Each oxalate unit is linked to central aluminium by 2 donor atoms, that is 2 oxygen atoms. Outside the coordination sphere, one can see K3, that is 3 potassium ion, and the valency of complex ion is satisfied by 3 water. So K3 and water, 3 water molecules, they are present outside the coordination sphere. Actually, this is also aluminate because the complex ion is negatively charged, and here there is a resonance between the donor oxygen atom. Any one oxygen can donate lone pair of electron to aluminium, and therefore there is not shown any arrows linked to aluminium by the oxygen, because the oxygen from the carbonyl group, any one oxygen can donate the lone pair of electron. This is in short the procedural per aluminium, pure aluminium in its shaving form. This aluminium in its shaving form is brought into hydroxide and then there is a reaction of potassium hydroxide with oxalic acid, and intermediate is formed, that is oxalic hydrate. For getting the product, we have to coagulate the product by using ethanol, ethyl alcohol. It helps to for coagulate product, and finally we can see the white color form, which is filtered funnel to get the solid complex, that is potassium trioxalato. Again, for calculations we need molecular weight of the complex, which is 462.7. Then the supplied W, that is weight of the metal uh, impurity mixed, major component mixed with impurity. So we require both these for calculation, and then we can calculate. So here we end with the preparation part, and the second set of experiment is general outline of quantitative and qualitative. Quantitative and qualitative analysis is again divided into two parts. Quantitative analysis, we are following volumetric titration method. Qualitative analysis, here it is a detection of impurity cation and impurity anion from the structure. The scheme of second part, that is quantitative and qualitative analysis. Now dear students, here one has to note that even during viva the entire scheme of quantitative and qualitative analysis can be asked. So one should know in short the scheme of how will you analyze the given salt for quantitative and qualitative analysis. Now here you will be given a mixture of two water soluble inorganic salts, let us say A and B. A will be major component and A will be known to the students. At the time of exam, the examiner will tell the students what is the major salt or the major component. But salt B, that is impurity salt, will not be disclosed to the students. So impurity component is not told, but students are aware which is the major component, which salt is the major component, that will be known to them. Major component will be quantitatively analyzed first by carrying out the titration. After that, qualitative analysis of the same mixture will be carried out for the detection of impurity salt. Only transition metal ions are included as major cations to be estimated quantitatively, and impurity salts added include either ammonium or potassium salts to be detected by qualitative analysis. Now here for semester 5 there are transition metal ions, but for semester 6 there are main group ions included as the major cations. So for semester 6 you can have magnesium, barium, calcium, strontium as the major cations. In qualitative analysis, detection of one cation and one anion from the impurity salt is expected. There are three major salts to be estimated in semester 5, that is transition, that is copper, Fe, nickel. For semester 6 we have barium, calcium, strontium. Impurity salts added are ammonium chloride, potassium nitrate, potassium chloride, potassium sulfate, ammonium nitrate and Ki. So from these given salts there will be mixing of salts, one major component and one impurity component. This is the flow sheet diagram, that is initially mixture of A plus B, major and impurity salt. Then first step is quantitative. By volumetric titration you will determine percentage purity. Then you will follow it by qualitative analysis, wet test analysis, determination of impurity salts, cations, ammonium or potassium. Either it will be ammonium or potassium. Never you will given the two salts That is, never you will be given the two cations for detection, only one cation as the impurity cation to be detected. Wet tests are carried out using water extract. So one has to prepare first water extract before proceeding for qualitative analysis. Now here only the quality, that is the detection of impurity anion and cation will be checked. There is no measurement of any quantity and therefore it is qualitative analysis. For preparation of water extract, given mixture is to be taken in a test tube. To that, small amount of water to be added, stir it very well and ensure that saturated solution is formed, which is treated as the water extract. Now remember, there is a difference between solution and water extract. Water extract is always a saturated solution. So once it is formed, you can divide that water extract into two parts, one for testing cation and one for testing anion. So analysis of impurity cation and the confirmatory test will be carried out, and then one can go for impurity. For the impurity cation, as per the syllabus, two impurity cations included ammonium and potassium. You can carry out the test for detection of ammonium ion and potassium by referring the handbook and the given test, that is few drops of water extract to that 5% NaOH solution to be added. Boil it strongly. If there is evolution of ammonia, smell of ammonia will be prominent, then the moist turmeric pepper will turn brown. If there is no evolution of ammonia, no smell, then ammonium plus is absent. If ammonium plus is absent, that means there should be present potassium ion. For that, take a fresh water extract. Then to that you will add 2 normal acetic acid and 5% sodium cobalti nitrate solution. Then at that stage, after heating, if you get yellow precipitate, then report potassium is present. Now this test can be replaced by one more test, that is, when ammonium ion is absent, then to the fresh water extract you can add picric acid in alcohol, slightly heat, and you will obtain the picrate derivative, that is a yellow precipitate. You will record potassium is present. CT for ammonium and potassium ion. Ammonium ion, we are using Nessler's reagent. To the water extract, add Nessler's reagent. If you get brown PPT, ammonium ion is confirmed as impurity cation. If potassium is present, then again the same test treated as confirmatory test, that is picric acid in alcohol giving you picrate derivative, which is a yellow PPT. So potassium is. After detection of one impurity cation, move to detection of anion. For that we will use the second part of water extract. There are total 4 anions included in our syllabus: sulfate, chloride, nitrate and iodide ions. Now remember one thing here, my dear students, whenever major component is provided to you, which you have already analyzed in quantitative analysis. For example, the major component is magnesium sulfate. That means sulfate ion is already present along with magnesium ions, and therefore you will get the test for sulfate ions in the wet test. But that doesn't mean that sulfate ions are the impurity ions, because sulfate ions are associated with magnesium in the major salt. Therefore, do not treat sulfate ions as the impurity. This is just the example. So accordingly, you have to check carefully which is the major salt. If it is calcium chloride, then chloride ion is not the impurity anion. Impurity anion will be different from chloride. If the major salt is magnesium nitrate, then that doesn't mean nitrate is impurity anion. Impurity anion will be different from nitrate. So accordingly, one should be very careful while detection of impurity anion. Suppose you are given a salt of magnesium sulfate and potassium nitrate. That means magnesium sulfate is the major salt. You will detect magnesium by quantitative analysis, volumetric titration. But sulfate ions, you will get the taste of sulfate ions with water extract. It is obvious because it is present in the mixture. But do not write sulfate present as the impurity anion. So if in that case you get sulfate ion, in the bracket you will write from major salt. Okay, your impurity anion is different from sulfate. It may be chloride, it may be nitrate, it may be iodide. So move further for chloride ion test, for nitrate ion and for iodide ion. So remember, this is a very important note that whenever the anion which is associated with major cation, that should not be reported as impurity anion. That care is to be taken. So this is all about detection of cation and detection of anion as impurity cation and impurity. Report the result. There are two parts. Part A, quantitative analysis. Here you will report percentage purity of, this is the example like copper sulfate 5H2O, or it is magnesium sulfate twice H2O, whatever it is. So percentage purity of the given mixture, that is equal to dash percent. And part B, it will be qualitative analysis, that is impurity cation and impurity anion you will have to record. So here we end with entire analysis, that is quantitative analysis and qualitative analysis. So here in quantitative analysis we are reporting percentage purity, qualitative analysis by wet test method, qualitatively we are detecting impurity cation and impurity anion. All the best for your practical exams.